Welcome to the rigid body equations of motion, a discussion based on the fifth chapter of Herbert Goldstein's classical mechanics. Today we are going to discuss a brief overview of the chapter, and then we are going to follow up with the preliminaries of motion about the point. As a short review, insofar, the kinematical tools that we've developed for the study of rigid body motion are as follows. The Euler angles, which are three generalized coordinates describing the orientation of a rigid body. The techniques of orthogonal transformations in matrix algebra, which are useful in investigating the characteristics of rigid body motion. And equation 486, which I will sketch up here. So the time derivative of a vector in the laboratory frame is equal to the time derivative of the same vector in the body frame plus the cross product between the angular velocity of the rotating frame times the vector. So this is the fundamental kinematic law relating the rate of change between space and body sets of axes. These will be used to derive Euler's dynamical equations of rigid body motion and to study simple but very general applications. Now we are going to discuss angular momentum and kinetic energy of motion about a point. Previously we mentioned Chalet's theorem, namely that any general displacement of a rigid body can be represented by a translation plus a rotation. The motion is parametrized by 6 coordinates, 3 Cartesian coordinates of a point fixed in the body for the translation plus the Euler angles for the motion about the point. If the origin of the body frame is in the center of mass, then by virtue of equation 128, the angular momentum decomposes in separate terms for the center of mass motion plus motion about the center of mass. These separate the two sets of coordinates, the Cartesian ones for the former and Euler angles for the latter. From equation 1.31, a similar decomposition holds for the kinetic energy, namely a separation in the kinetic energy of the center of mass plus kinetic energy of the motion for the system as a whole about the center of mass. A similar decomposition generally holds for the potential energy as well. In a uniform gravitational field, the potential energy depends only on the vertical Cartesian coordinate of the center of mass. As another example, if the force is due to a field of magnetic induction B acting on a magnetic dipole moment m, then the potential is proportional to the dot product between m and b, which involves only the orientation of the body. In such cases, the mechanical problem splits in two parts. The Lagrangian, which is just the difference between the kinetic and potential energy, will involve a purely translational and a purely rotational part. With the corresponding variables separated, the two problems can be solved independently of each other. In order to begin the discussion, we must first show that all points of a rigid body rotate with the same angular velocity. And this might sound like something that is very trivial, but in fact the proof is quite subtle, and it will follow the reference given here in terms of an article published in the American Journal of Physics in the year 2000. We begin by assuming that we have two coordinate systems, sigma 1 and sigma 2, which are attached to a rigid body at the points r1 and r2, capital vectors, which serve as the origins O1 and O2 relative to O, which is the common origin of the laboratory and body set of axes. Assuming that these frames rotate with angular velocities omega 1 and omega 2, we can write the difference between the vectors r2 and r1 as the vector r, and from this we can calculate the time derivative of this expression in two ways. So we can solve it either for r2 and r1, and in each case, knowing that r is invariant in the body set of axes, we can apply the formula 486 to its time derivative. So this is written implicitly in the laboratory frame, and it is equal with the expression here and respectively the one here. And then if we just put these two expressions together, we obtain the result here. However, in spite of appearances, it does not follow from this equation that omega 1 and omega 2 are equal, because based on the fact that r is arbitrary, because the problem here is that if we change r, we in fact change either one or both of these angular velocities. They are not independent of the choice of r because of this constraint. So to find the correct proof, we need to add an additional point b, which has the coordinates r1 and r2 written with a small letter relative to O1 and O2. And then we can write the distance from P to the origin, or the vector r, again in two different ways, and we can once again calculate its time derivative and use the fact that r1 and r2 do not change in the body set of axes to obtain the expressions here. And if we put them together, we obtain this result, which is indeed written in terms of an arbitrary vector that is independent of omega 2 and omega 1. However, this proof is still incorrect, and it is incorrect because the cross product here is perpendicular to r. So we have only shown that the two angular velocity vectors differ by a vector that is proportional to r. In order to give the correct answer, we need to put three things together. Namely, we need to realize that we can write capital R as either the difference of these vectors or these two vectors, and take results 4 and 5, which we have deduced here, together with this expression. And in doing so, we obtain the first line here, the result 7. And furthermore, so this time derivative up here needs to be is equal with this expression. So again, putting the two together, we obtain the result 9, and then we combine this with the fact that r can be written as the difference here. And then finally, what this does, it leads us to this result, which indeed concludes that omega 2 and omega 1 must be equal given the completely arbitrary nature of R2. For a rigid body moving in such a way that a point remains stationary, the angular momentum has the expression here. And now from 486, we know how to write the velocity vectors associated to each particle I, and if we put these two results together, we can rewrite the angular momentum vector in a slightly more involved way, which is given here. Now, if we write each component of the angular momentum down, for example, I've written the x component here, what we observe when we expand this expression is that each component is a linear function of the components of omega. So it's a linear function in omega x, omega y, and omega z. Thus, the angular momentum vector is related to the angular velocity by a linear transformation, which can be written explicitly as in the set of equations here. And the diagonal terms involved in this expression, the ones given here, for example, are known as the moment of inertia coefficients, while the off-diagonal terms are the products of inertia. These results hold for rigid bodies made from a number of discrete particles, and for a continuous mass distribution, the summation turns into an integral over the body's density. So the first diagonal component, for example, has this expression, and a general component is given by the expression here. Henceforth, we will mainly consider coordinate systems fixed in the body. In this case, various distances are constant in time, and so are the matrix elements, which become specific to the body involved and dependent on the origin and particular set of axes chosen. So what we have shown in these circumstances is the relation here, which says that the as of yet, let's say, not fully specified operator I, having dimensions of mass times length squared, acts on the vector omega in order to produce the new vector L. In summary, we have reviewed the kinematical tools used in the study of rigid body motion. We have proven formally that all the points of a rigid body rotate with the same angular velocity, and for rigid bodies having a fixed point, we have established the linear transformation between omega and L, and have found the general form of the matrix elements. In the following, we are going to discuss in more detail the nature of the operator I, and as such we are going to discuss tensors. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.